Hello, class. This is Professor Muller again. Today's lecture topic is going to be section 4.2, number bases in positional systems. So what does that mean? Sort of a fancy term or fancy language there. Remember, for positional systems, we more commonly call it place value systems. And when we talk about number bases, we're now talking about bases other than 10. So in the 4.1 homework, we talked about our number system, Hindu-Arabic, which is base 10. We also talked briefly about the Babylonian number system, which is base 60. Something that I didn't talk about in 4.1, this is not in the homework, is the Mayan number system. They were base 20. And so throughout our history, there's been a lot of other bases used other than base 10. That's just the one we're used to. And so what we're doing in 4.2 is we're going to be seeing how to do the arithmetic to change from base 10 to a different number base or vice versa. And I think this, particularly, again, as I mentioned, I think on 4.1, these are really kind of geared towards education majors, this whole chapter. If you're computers and you ever heard about the zeros and ones, that's a binary system. But I think by going outside our base 10 number system, it gives you a little bit more appreciation for our number system that we actually use. All right. So we're really kind of only doing two topics at 4.2. How do we go from a different base to base 10? And how do we go to base 10 to a different one? So let's just jump into the notes and get going. Yeah, this is definitely a different style than chapter 2 and chapter 3, where we had to learn our definitions. Now we're getting into like core arithmetic ideas. There's a little bit of a change of pace. Some people like it. Some people prefer the logic, but we get to do a little bit of everything in this class. Okay, so number bases. So when we talk about the base, binary is base 2, octal is base 8, hexadecimal, and both binary and hexadecimal are important in computing. Hexadecimal is base 16. We talked about the Babylonian, which is base 60. I briefly mentioned the Mayan system, which is base 20. One of the interesting things about the Mayan number system, I think that was like historically one of the first number systems that actually had its own symbol for zero. Believe it or not, zero, particularly as having a symbol being important, was something that came kind of late in the development of a lot of our number systems. Totally different aside, but um, since we're talking a little bit about the history in this chapter, I just want to throw that out there. Okay. The key point in 4.2 and also 4.3 when we're dealing with the arithmetic of this is the base of the number system is the position of those numbers is based on powers of that base. So we talked about this with expanded form for base 10 is we start with the ones place value, and then as we go to the left, it's the tens and the hundreds and the thousands and the 10,000s. That's coming from 10 to the 0, 10 to the first, 10 to the second, 10 to the third, and so on. And again, we're not dealing with decimal numbers here, so we're not have to worry about that. But we're starting with the ones place value, moving to the left. So in a binary system, which is base 2, we're dealing with powers of 2. So 2 to the 0 gives us 1, so we're just going to call that the ones, like in all these systems. And then as we go to the left, it's 2 to the first, 2 to the second, 2 to the third. And so those are the position values of those numbers. It's no longer 10 and 100 and 1,000. It's 2 squared is 4, 3 2 to the third is 8, and so on. For an octal system, that's base 8. So on the right, we're always going to start with the ones. And then as we move to the left, it's 8 to the first, 8 to the second, 8 to the third. Those are the values of the digits in those places. Okay. So, with the example, I think I used 4.1 is 732. In our number system, 732, the 2 means ones, the 3 is the tens, the 7 is the hundreds. Well, if we're an octal number system and we had 732, the 2 would still be the ones, but now the 3 would be values of 8, and then the 7 would be 8 squared, which is 64. Okay, so we're dealing with we're not dealing with powers of 10 with these numbers. Now, one thing to keep in mind, how do we know what base we're dealing with? We're going to use subscripts to the right of the number. Sometimes we'll write them out in English form. Sometimes we'll just put a number. But if you see these subscripts, that's the base that we're dealing with. So, those are base 8. For binary, that's base 2. We'll either do a little subscript of 2 or write 2 out. If it's hexadecimal, which I don't think I put any of those in there in the homework, there'd be a little 16 subscript. If you don't see a subscript, then we're assuming base 10. Sort of like a square root, we don't put the 2 above the square root, but we have to put a 3 for cube root, things like that. So if you see no subscript, it's base 10. All right, so what we're doing in 4.2 is we're going to either convert from one base, other than 10 to base 10, or we're going to start on base 10 and go to a different base. Okay, so the way this works, it's easier to start by converting to base 10, and because that's more multiplication addition, whereas the other way is division. So let's start. How do we convert from, say, base 2 or base 8 or base 16 to base 10? Okay, so same 3 basic steps, no matter what base we're using. So step 1, using the powers of the starting base, convert the original number to expanded form. So you know what expanded form is, right? So that's how many ones do we have, and base 10 is how many tens do we have, how many hundreds do we have, how many thousands do we have. Key here is now we're no longer in base 10 for our starting base. So now instead of tens, hundreds, thousands, we're dealing with 2s, 4s, 8s, etc. So that's the first step, is we're going to write out our number in expanded form. Then what we have to do is, using those powers and associated digits, we need to figure out the actual numerical value in base 10. It's like over here, that's 2 to the first is 2. So we're going to have to do 2. If we're in a binary number, we'd have to, if there was something in the second spot, it'd be 2 times that number, that digit. If their number was in the third digit from the left, it'd be 2 squared is 4, so it'd be 4 times whatever that number is, and so on. This probably make a little bit more sense when we have numbers to put to it. But basically, once we put it in expanded form with powers over here, then we got to convert these powers to actual base 10 numbers. Okay. Once we do that for each place value, then we just add them all up, and then there's our number. Okay, so really the key is those first 2 steps. The last step is just addition. Okay. And this is why in 4.1 I had to do a lot of expanded form problems. So because we need it in here. Okay, so number 3, convert the numeral to the given numeral to a numeral in base 10. So we're going to start with 45 base 8. Okay. So what does 45 base 8 mean? Well, this is why we need the expanded form. So step 1. So the 45, and go from right to left. The 5 is the ones place value. So it'd be 5 times 1 plus the 4. 4 times what? Well, we are base 8. So it'd be 8 to the first. So just like when we were doing base 10, if I can find my examples from last time. Well, I get it over here. So on the right is always the ones place value. Then as you go to left, whatever your base is, it's that base to the first, then to the second, then to the third. If you had like 10 numbers, you'd be like 10 to the 9th or 2 to the 9th by the time we're done. Yeah, so that is expanded form. 8, the 1 spot, and then 8 to the first. If there was a third digit, that would be something times 8 squared. That's step 1. Just write it in expanded form. Step 2 is using those powers and associated digits, compute the value in base 10. So basically, what is, go on the calculator, what is this? Well, this is just 4 times 8, which is 32, plus 5, which is 37. Now, I'm going to put a base 10 in the notes just for emphasis. Remember, we don't have to put the base 10, because if we don't put a base, we assume that 10 is the base. So 45 in base 8 is equivalent to 37 in base 10. There. Now, I'm going to write this on a scrap paper because that way, because I don't want all my problems to run together. So we look at number 4. We have 22 base 5. Now, notice they're writing the word out. I'm just for out of habit, I'm used to writing the number itself rather put in English. It can be either way. Okay, so but we have 22 base 5. So what does this mean? So step 1, put it in expanded form. So I like to start on the right because the right is the ones place value. So that is 2 times 1 plus 2 times what? Well, we're in base 5. What's the exponent? Well, remember this is the 1 is 5 to the 0. So we start with the 0 exponent. So this exponent is to the first. So that second column or second digit on the left is always to the first power. Okay, then step 2, now we do the arithmetic. Well, this is just 2 times 5 plus 2, that is 12. And again, just for emphasis, I'm going to put the base 10. So 22 in base 5 is equivalent to 12 base 10. So that's sort of like 22 base 5 is like if you only had one hand and you had to count, then you do 1, 2, 3, 4, 5. And then you'd have to like start over. And so 6 would actually be 1. So there's 5, and then if you want 6, then you got to put your finger down. So like you're starting over because you're reusing fingers. Where if we're counting base 10, we don't have to count over until we get through all 10 fingers. Then 11, 12. So that's kind of what we're doing here. Okay. So that is, let's do a little bit longer number, more than 2 digits. So number 5, we have 231 base 4, and we need to convert this to base 10. So step 1, convert this to expanded form. So start on the right, because that's the ones place value. So we have 1 times 1. Now the second column, we're in base 4, so this is going to be 3 times 4. The second column is always to the first power. Now we have the third column, so that's 2 times, or base 4. What's the exponent on that 4? Well, we had 0, 1, now that is base 2, or exponent 2. Okay. So the ones is, remember, that is 4 to the 0. So then we have 4 to the first, and 4 to the second. Now we do the arithmetic. And we talk about this in order of operations. This is where do not multiply before you do the exponents. Do the exponents first. So that's 2 times 16 plus 3 times 4 plus 1, or 32 plus 12 plus 1. It's at 44, 45. Okay. So that is, 231 base 4 is equivalent to 45 base 10. Let's do some binding. So number 6 is we have 1101 base 2. We want to convert this to base 10. So let's put this in expanded form. So 2 is our base, so we're doing powers of 2 for our place values. Start on the right, we have 1 times 1. Then we have 0 times, well, times what? So the base is 2. The exponent on that second column is always the first. Now for the third column, that is 1 times 2 to what power? Well, it's 2 to the first. Now that's 2 squared. I guess if I start on the right, sometimes we're out of room, but that's kind of the way it used to work in. So this fourth column, that 1 times 2 to what power? Well, we did 0, 1, 2, now that's to the third. Yeah, if working backwards is a little confusing, just, you know, just, you know, you might want to make a note to yourself. That's, so the exponent is 1, 2, 0, 1, 2, 3, 3. And so if you do that, then maybe you can start with 1 times 2 to the third and then 1 times 2 to the second. Yeah, just play around with this. That's why you do the homework, to kind of see what works best for you. But again, this all comes back to place value. Place value is always based on powers of a number, and the base that we're talking about is always, the number system itself. All right. So now we just do the arithmetic. So 2 cubed is 8. So that's 1 times 8. 2 squared is 4. Well, that's 0, 1. Now you don't necessarily have to write every single step out, particularly as you get more comfortable with it. And again, for the notes, I'm going to write all this out. So that is 12, 13. The 1, 1, 0, 1 base 2 is 13. Now let's see. Let me do this same number, but in a different base to kind of show you, maybe that'll help a little bit. So this one's not on there, but let's do the same number. So it's 1101. But now let's do this base of 7, just because. So what does this mean? So let's try starting on the left and working our way over. But if you do that, you still need to kind of know what the power is. So start on the right. The powers on our base are going to be 0, 1, 2, 3. Those are our exponents. So the first number is going to be 1 times the base, which is 7, to the third power, and plus 1 times the base, which is 7, now to the second power, plus 0 times the base, which is 7, to the first power, plus 1 times, well, 7 to the 0, is 1. So remember, on that last one, we always just put 1. So now we have some arithmetic that short calculators come in handy. And was it 343? Yeah. So that's 1 times 343 plus 1 times 49 plus 0 times 7 plus 1. So 343 plus 49 plus 7. I'm sorry, plus 0. That's probably an easy mistake to make that I just did there. So I was thinking 7, my brain said 7, but we have 0 times that, so that is 0. And now we put the it's 393 base 10. So let's compare those. So 1102 base 2 and base 10 is 13. But 1101 base 7 and base 10 is 393. Okay. And so why is this number so much bigger than the other number? Because in this number system with base 2, we're doing powers of 2. In this other example, we have powers of 7, and clearly, powers of 2 are going to not be as big as powers of 7. So the bigger the base, the bigger the numbers grow. But notice they're both, in base 10, that would be 1,110. The reason these are both smaller than 1,101 is because the bases are smaller than 10. If we did something like in hexadecimal, where it's base 16, then we're going to get a number that would be bigger than 1,101 because the base is now bigger than 10. That makes sense. Okay. Let's do one more of these. Let's test and see how good you are with keeping track of all our exponents. Again, I'll do this on a different sheet of paper. So this is 101 and then 101 base 2. So let's convert this to base 10. Yeah, this is where if I started on the right, work to the left, I've definitely run out of room. So, we know our base is 2. So what are the exponents going to be? So I like to start over here on the right. That's always going to be 0 and 1, 2, 3, 4, 5. Okay. So these are exponents. So what do we have if we write this out in expanded form? So we have 1 times our base, which is 2 to the 5th power, and then plus 0. In this case, since I'm multiplying by 0, I'm just going to say 0. So, and then we have 1. Now, what are we multiplying it by? Base is 2, exponent is 3. We have 1 times base is 2, exponent is 2, plus 0. And then we have a 1, that's in the 1 spot, so just times 1. So now let's do some arithmetic. 2 to the 5th, what is that, 32? Yeah, so that's 1 times 32, that's 0. 2 to the 3rd is 8. 2 squared is 4. And again, if you want to go ahead and like do 1 times 32, not write that step out, that's fine. I'm just for the notes. I'm trying to write out every step. I don't want to skip the step that people might need. And then just add all those up. So what's that? 40 plus 5, so 45. Base 10. Oh, and again, in MyMathLab, if you just put 45 and don't put the subscript, it'll be fine. Because again, if you don't put the subscript, it will assume base 10. All right, that is how you convert from a base that's not 10 to a base that is 10. Right? So you write it out in expanded form. You need to make, the place values. You need the base of the number system to some power. So that base will be the same every single time. So this is base 2, so those were all base 2. And then the exponent starts at the 1's place value, which is a 0 exponent, and then just count up as you go to the left. Now, how do we go the other way? So how do we convert from base 10 to a different base? Well, this is more complicated, which is why we're doing this second. But think about this. If we're basically going backwards. And so we were doing multiplications initially, or powers to convert this. So since we're going backwards, we're going to be doing some divisions. What we're going to be doing with the divisions is we're going to have to figure out like how many like exponents we need. How big do we go up? Like if we're converting a number in base 10 to base 2, can we stop at 2 squared? Can we stop at 2 cubed? Do we have to go up to 2 to the 5th? So the whole purpose of all these divisions we're going to do is one, what are, like we're trying to figure out this part of the expanded form. So not only, so we're associating, we're doing that, and we need to figure out these digits. That's the big thing, the division for us. It gives us those digits in front of the powers. So how does all this work? All right, I'm going to read through the steps, but it's always helpful to kind of put the steps, the English part of this to words, especially since these are kind of wordy. So once I read through all this, then we will definitely do examples with numbers. So just kind of bear with me. Okay. So for the new base, we need to start listing powers of that base until we get a number larger than the original number to be converted. All right, so for example, if we're going to convert 83, now notice there is no subscripts, that's base 10. If we want to convert that to base 5, we need our powers of 5. Powers of 5, 5 to the 0 is the 1s, 5 to the 1st is 5, 5 squared is 25, 5 cubed is 125. Now we can stop because 125 is bigger than 83. So we don't need the 125. We need the 1, the 5, and 25, but we had to figure out how big to go. Once you get one that's, I don't know if you all watch The Price is Right at any point, but you want the closest number to it without going over. Once you go over, we can stop. at least for the powers part. Same there with 89. When we're going to convert 89 to base 7, we need powers of 7. So the first power is always 1, because 7 to the 0 is 1. And then 7 to the first is 7. 7 squared is 49. 7 cubed is 243. Wait, is that 243 or 343? Oh, 343. Right. But 343 is bigger than 89, so we don't have to keep going. So we're not going to need 7 cubed. We will need the ones, the 7 to the first and the 7 squared. So that's what I mean here is, we need, when we say start listing powers of that base, so we get the number larger, that's what I'm talking about. Okay, step 2, using the largest power of the base that fits, do long division on the original number with that base. Okay, so what that means is like here for 83 to base 5, the largest number or the largest power of 5 that is less than that is 25. So we're going to do long division with 25. That's where we're going to start. You always start at your biggest one and work backwards. So when we're going to convert 89 to base 7, 343 was too big. So the first division we're going to do on 89 is with 49. And when I say long division, that means we need a whole number answer and a remainder. We don't want the decimal. And so if you're going on your calculator and doing this division, you're going to get the decimal. So you got to know how to convert the decimal to the remainder or how to get the remainder. You can use your calculator to get the whole number part, but you have to play a little bit to get the remainder. And we'll discuss that. Okay, so taking the remainder, divide it by the next smaller power of the base. So basically the remainder from the first step is going to be what we're going to divide by the next smaller number. So we're going to divide 83 by 25. We're going to get an answer. And then that remainder, we're going to divide by 5. For 89, we're converting to base 7. We're going to first divide it by 49. The remainder that we get, then we're going to divide it by 7. That's what step 3 is saying. Step 4, repeat step 3 until the remainder number is smaller than the base. So what we're going to do is, we're going to take, number 9, we're going to divide 83 by 25. The remainder we're going to get, we're going to divide by 5. We're going to get another remainder. We're going to divide that by 1, and then we're done. Because you can't, we don't have anything smaller than 1. Because we're not dealing with decimals. Okay, so after you do all your divisions, how does that give us an answer? So the answer, listing those division answers from left to right, because remember we started with the bigger number. So the bigger number in numbers is always on the left because those are the biggest place values. Basically, we're going to put these in reverse order. So we're going to start with that first division on the answer on the left, and then we're just going to count down our division answers. So like on these, if we have to do 3 divisions, we should have 3 digits in our answer. If we have to do 4 divisions, we'll have 4 digits in our answer. And then the last thing that you don't want to forget, because this is an easy thing to have MATLAB catch you wrong, you have to put the subscripts on these answers because our answer is no longer base 10, it's base 5 or base 7 or base 4 or whatever we're converting to. All right. Let's put all of this into practice. So I'm going to go over here on a different sheet of paper, just make sure I have room. So we are doing converting 83. And again, there is no base. So just for emphasis, I'm going to put the 10 there to base 5. So step 1, list our powers of 5. So 5 to the 0 is 1. 5 to the first is 5. 5 to the second is 25. 5 to the third is 125. Yeah, if you need a calculator to get these, that's no problem. 5 I've been dealing for a while, so I know those. But once you get one that is bigger, then stop, because we don't need the one that's bigger than our number. So that's the first step. get these powers of 5. If you want, you don't have to put the 0. You can just start with 1. I kind of like doing that because then you're doing 0, 1, 2, 3 on your exponents. But that first one is always just the ones place value. Okay, so that was step 1. Step 2, using the largest power of the base that fits, do long division on the original number. So now we're going to do long division on 83 with 25. That's step 2. We're doing 83 divided by 25. And again, it is perfectly acceptable to use your calculator, but here's what happens. When you do 83 divided by 25, you get 3.32. So we want the 3, but we don't want the decimal. So if you haven't done long division in a while, which when we converted improper fractions to mixed numbers and vice versa, we did a little bit of this. So other than that, again, I realize it may have been a while since you've done this. But when you have the 3 times 25 is 75. You subtract that and we get 8. So we don't want 3.32. We want 3 remainder 8. So that part of it, that 3, we need to keep that for later reference. So what do we do next? Take the remainder and then divide it by the base of the next smaller power. So we've done division with 25. Okay. Now we need to do division with 5. So what are we doing division on? You take that remainder, and that remainder is what goes inside your division. So we're going to divide 8, and we're going to do it by the next smallest one that we haven't used yet, which is 5. Well, how many times does 5 go into 8? 5 goes into 8 once, with a remainder of 3. So again, keep track of that 1, and because we'll need it later. So now what do we do? Well, we've done division with 5, and so now we got to do division with 1. Now I'm going to write this for this example, but at this point, we probably don't have to write this out. After we see it once, we're going to take that 3, that's going to go inside division. We're doing 3 divided by 1. So that last step, the remainder is like the answer. The remainder from the last one is the answer. Okay, but we have 3 powers that we need, so we need 3 divisions. Right? Even though that last division is always just going to be whatever that remainder is, because we're always dividing by 1. Okay, so now what? So once we get down to 1, dividing by, we're done. So the answer is listing those division answers from left to right, starting with the biggest one and working our way down. So start with the 3, go to the 1, go to the 3. And then the last step, don't forget to put the base as a subscript. So we're going to base 5. So 83 base 10 is 313 in base 5. And I know, like I said, this is definitely more complicated, I think, than the converting to base 10. But we're going to do all these problems the exact same way. And one of my philosophies, no matter what we're doing, is if you can be systematic in your approach, kind of do do the same thing every single time, no matter how big or messy the problem is. If you can do it with smaller numbers, then as you get to bigger numbers, it works out the same way. Again, I really wish I could take questions from the audience. I can't do that now, so we just got to go into the next exam. All right. And I really hope people are watching the video on this, because this is something that I imagine almost nobody has done this recently. So there's definitely I'm assuming that this is a brand new topic for everybody, trying to explain everything. All right, so we're converting 89 base 10, and again, I'm putting the 10 for emphasis, even though it's not in the original problem, to base 7. So how do we start the conversion? Step one is we always need our powers of whatever our base is. So start with 7 to the 0, that's our ones. And again, if you're comfortable with that, you can just put the 1 there and not do the 7 to the 0, but it doesn't hurt to me that we're being consistent. So then we need 7 to the first, which is 7. We need 7 squared, which is 49. We do 7 cubed. This is where I had it wrong on the paper. I had 243, but it's 343. Now notice that is too big. So we can stop. So we only need up to 49. So how do we use this? This is where we do our divisions. So we're going to divide 89. What are we going to divide 89 by? Always start with your biggest power that's not too big. 343 is too big, so we're going to divide by 49. I could do that in my head eventually, but again, this is where calculators come in handy. Okay, so 89 divided by 49 is 1 point something. Again, we don't want the decimal. So 49 goes in 89 once. So now just do the long division. 1 times 49 is 49. We get 40. And so that 40 is our remainder. So circle that 1. That's part of our answer. Now what do we do? You take that remainder. That is what we're going to divide next. So we've divided by 49. Now we could divide by the next power up. So now we need to divide by 7. So you can see why I like writing it out this way, is to me it helps keep everything ordered. So we're going to do 40 divided by 7. Okay, so that is 5 point something. So that is 5. Let's see, sometimes 5 is 35 minus 5. That is 5, remainder 5. So circle that 5 because that's important. We have a remainder, so we got to keep going. So what are we going to divide this time? We bring that remainder down. We're dividing 5. What are we dividing 5 by? Well, we did division by 7. Now we're going to divide by 1. Well, 5 divided by 1 is 5. There is no remainder. So we've done our last division. But that answer is still important. All right, so how do we use this information to convert 89 to base 7? So remember, on the left is always our higher power. And so we take our higher power answer and go to the right. So this is 1, 5, 5. We're in base 7 because we're using powers of 7. So don't forget your subscript of 7. Okay. And I really wish I could hear questions. At this point, I just kind of have to keep doing examples. All right, let's see. And again, we don't get too messy with this. Let's do 11, 12 doesn't really matter. Let's do 11. And then we'll call it good. No, let's do 12. That might have a couple more divisions to it. Okay, so I'm sorry, let's do 12. So now we're going to convert 359 base 10 to base 2. So what's the first step? Is we're converting to base 2, so we need powers of 2. So we have 2 to the 0. So that first one is always 1, because anything to the 0 is 1. 2 to the first is 2. 2 squared is 4. 2 cubed is 8. 2 to the 4th is 16. 2 to the 5th is 32. So we definitely have a few divisions to do here, right? So we'll let's do one of these messy ones together. So we got to keep going. 2 to the 6th, well, we're just multiplying everything by 2. If you need your calculator, great. I'm a little bit more comfortable with these. 2 to the 6th is 64. 2 to the 7th is 128. 2 to the 8th, what is that? 256. 256. So we're still not there yet. Let's pick this example. All right, 2 to the 9th is 512. So we finally got one that is too big. So we can stop. All right, yeah, I picked a good one, right? So we got to do 1, 2, 3, 4, 5, 6, 7, 8, kind of 9 divisions. That last one doesn't really count, but we still need it. So we're gonna have several divisions to do here. So this may not have looked like it, but this is probably like the messiest conversion in here because of the number of divisions we have to do. So where do we start? Always start with your biggest one that's not too big. So we're gonna take 359. We're gonna divide it by 256. Okay. How many times does that go in there? Well, the nice thing about binary is we're only dealing with zeros and ones, so this is only going to go in 0 or 1 time. But when in doubt, go to your calculator. 256 goes in there once. 1 times 256, 256. So now we need the remainder. 103. So circle that 1 as part of our final answer. So now what do we do? So now we need our next division. And so we do our next division. We always take, I'm going to put my divisions in. Take the remainder. That's what we're going to be dividing. And what are we going to divide with? We've used the 256. Now we have to do 128. All right, how many times does 128 go into 103? Well, if you're thinking it doesn't, you didn't answer my question. My question was, how many times does 103 go into 128? It goes in 0 times. So it's not that it doesn't go into it, it goes in 0 times. That may seem a little weird to say. That's also why it took our civilization thousands of years to come up with a symbol for 0, because it's a little bit harder concept. So 128 goes into 103 0 times. Well, what's the remainder? Since we didn't subtract anything, the remainder is 103. Again, circle that 0 because that's part of the answer. Okay. Now again, remainder is what goes on the inside. So we've divided by 128. Now we have to divide by 64. And times does 164 go into 103? Well, only 1. You know, if you're dealing with binary, if you're dealing with powers of 2, these answers are always going to be 0 and 1. Okay, something I didn't point out, now that I'm thinking about it, when you're dealing with binary and your bases, your digits are 0 and 1. If you're dealing with base 8, it's 0, 1, 2, 3, 4, 5, 6, 7. If you're dealing with hexadecimal, once you get past 10, then we start having letters. So one reason I didn't count for it. But since we're dealing with, like these numbers are the only possible answers to our division. So that's why with binary, our answers to division are always going to be 0 or 1. All right, back to the problem. We're doing 103 divided by 64. That will go in once. So 103 minus 64 is 39. We have 1 remainder 39. So circle that 0. It's part of our answer. So now what are we going to do? We're going to take that 39 and we're going to divide it. What are we going to divide 39 by? Well, we divided by 64, so now divide by 32. How many times will 32 go into 39? It'll go once. The remainder is 7. Circle that 0. And so now that 7 becomes what we're going to divide next. What are we going to divide 7 by? Well, we haven't used 16 yet. So how many times will 16 go into 7? Don't tell me it won't. Tell me it goes in 0 times. What's our remainder? 7, because we got 0. So I'll go to 0. That's important. So now I'll take that remainder. We're going to divide 7. What are we dividing 7 by? Well, we divided by 16. So now we divide by 8. 8 will go into 7 0 times. So we have 0 remainder 7 again. So hopefully you're starting to get the hang of this. So now we take that remainder. We're going to divide 7. What are we going to divide 7 by? 4. How many times will 4 go into 7? It'll go in once. With the remainder 3. Now notice that I've very deliberately been like writing these down, try to keep them in order, because the order matters once we get our final answer. Right? If you're just haphazardly putting these all over the place, then it makes it a little bit harder to keep track of like the order that they go in the final answer. One reason I'm preferring to do this. Now I'm running out of room, so now I'm going to start going sideways, but I still want to kind of keep in order. And so we have a remainder 3. So we're going to do 3 divided by what? Well, we've divided by 4, so now we divide by 2. 3 divided by 2, it'll go in once. The remainder 1. Okay, so we still have a remainder, so we still have a division to do, but now we're doing 1 divided by 1, which is 1. Now we have no remainder, so we're done. Okay, so that was a lot of divisions. 1, 2, 3, 4, 5, 6, 7, 8, 9. But the nice thing about binary is all the answers are either 1 or 0, so that made the arithmetic of the division go a little bit quicker. But it is more to keep track of. The smaller the base, the more divisions you have to do. All right, so what is our answer? So we have all these answers to our division. Remember, if we're going from left to right, always start with the answer from the biggest divisor. So it's going to be 1, 0, 1, 1, 0, 0, and then 1, 1, 1. And this is binary, base 2. All right, that is probably the longest conversion that you might possibly have to do. If you're dividing, if you're doing base 7 or base 4, base 5, these numbers grow a lot quicker. So you're much less likely to have near as many steps. But that's to convert from base 10 to another base. First thing you need to do, get all your powers of your base until you find that power that is bigger than what your original number is. Once you find that one that's too big, then you don't have to go any further because we only want the one that's like just smaller than that. Then you start doing a series of long divisions, starting with your biggest power. And whatever your remainder is, the remainder is what gets divided the next turn. So to go to the next power, divide that remainder, so it just kind of keeps trickling down. And then your answer is start at the top, work your way down in your powers. Now, theoretically, we could go from we don't have to use base 10. We could go from directly from base 3 to base 5. I will save that for those of you that decide you want to be mathematicians at some point. I don't know, for education majors in math structures, they may have you do that. That gets a little bit more complicated. You could always like convert one base to base 10, like the first base to base 10, and go from base 10 to the other base, kind of do it in 2 steps. You could also do this in 1 step. That's a little more complicated. We don't need to do all that. Sort of like with the truth tables, I'm going to show you the basics of this and try not to get too messy. I'm feeling a lot of you like, well, you've already passed the too messy point, but we have to do some of the basic stuff. So, all right, that is 4.2. So 4.2 is all about converting from a base that's not 10 to base 10. And that's when we got to use just the expanded examples. Yeah, so that was where we were using expanded form to write it out in terms of our different powers. And then we were just doing arithmetic. So going to base 10 is a little bit more straightforward. Or if you're going to start at base 10 to a different base, then you got to do a series of divisions based on those powers. The only way to get this down is practice. All right, that's it. Next time I see you, we will be doing 4.3. And 4.3 is theoretically, adding, subtracting, multiplying, dividing. We're not going to do anything but the adding, subtracting. So we're really going to kind of tone down 4.3, and it's going to be a little bit short. But to be able to do the adding, subtracting, you have to have a feel for how to convert from one base to the other, because that will be helpful in a lot of those problems. All right. So have a good day.